Okay, so we've introduced this function n choose k, right? And remember how we defined it. N choose k is actually equal to 0 if k is bigger than n, right? Or n is less than 0 or k is less than 0, right? Just the oddball cases. Okay, otherwise, n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k, right? So this is a recursive definition, which means we can use induction to prove things about it, right? So here's one thing I want to prove. N choose k is always greater than or equal to 0, okay? So here's our base case, right? If any of those happens, then we're going to say n sub k is equal to 0, so yes, absolutely, it's greater than or equal to 0. And here's the inductive case. Well, using induction, then I can assume that this is greater than or equal to 0. That's greater than or equal to 0. And when I add two numbers that are greater than or equal to 0, I get a number that's greater than or equal to 0. Done. Okay. So that's the end of that proof. Okay. Pretty easy. Okay. Now here's another one. We know that it's always greater than or equal to 0, but it can only be 0 effectively in the base case. Okay. So let's see if we can prove this, right? So let's see. Let's say that n is not less than k, okay? Well, if n is not less than k, and n is valid, all the numbers are reasonable, then we're going to go down the induction step, right? But notice that if n is greater than or equal to k, then n minus 1 is greater than or equal to k minus 1, right? So I can now use my properties and say, well, that's not equal to 0, okay? And I know that the other half is greater than or equal to 0 anyway, so I'm not even going to reason about it. I got a number that's positive, and I'm adding a non-negative number. Done, right? So yes. That's the end of that argument, right? So here's another property, okay? Now, here's the fun one. N choose k is always a natural number, okay? Now, why is that? Well, base case, yes, it's 0. 0 is a natural number. Induction case, well, I can assume that n minus 1 choose k minus 1 is a natural number, and I'm also assuming that n minus 1 choose k is a natural number. Notice the really strong induction here, right? Okay, so since both of those are natural numbers, then when I add them, I get a natural number. End of proof, okay? So this is just kind of review of some of the induction stuff that we did, okay? How about this one? N choose k is equal to n choose n minus k, okay? That's actually a slightly more intricate proof, but it's not that hard, okay? So yeah, you could go ahead and try it. The base case is fairly trivial because it's either k greater than n or something is negative, right? And so in those cases, it takes care of itself. And then we have these really strong assumptions that we can pull, like n minus 1 choose n minus 1 minus k minus 1, right? So that's how we're gonna get that result, okay? All right, here is what I really want you to see, okay? This is something that we can actually prove, okay? And we can prove that n choose k is equal to this. If n is greater than or equal to k, greater than or equal to 0, right? So this is the reasonable case, right? Reasonable inputs, right? In those cases, then it's actually given by this formula, n factorial divided by k factorial times n minus k factorial, okay? And you may have seen that definition, kind of in a, pre-calculus course or maybe even middle school, where you talked about choosing things from elements. And absolutely, that's kind of the way that n choose k is usually defined, right? We didn't define it this way. We defined it using a recursive function, right? But we can prove that it's equal to that formula, okay? Kind of as a bonus, when we define it this way, we can only do it when we assume that the numbers are reasonable going in. In fact, we need to be careful, and if they're not reasonable, then the answer has got to be 0. Otherwise, things start falling apart. Okay. So I want to remind you of the very first ACL2 project we did. Okay, and we used this, and we defined it in ACL2. Okay, and I asked you to prove a few things about it, and one of those was proving that this was a natural number, right? And ACL2 was totally unable to prove that, okay? And here's why. It knows that that's an integer, okay? It's smart enough to know that n factorial divided by k factorial is actually an integer, right? Because, well, you have n times n minus 1 times and so on until you get to k plus 1, so we can kind of do that. But then, why is it the case that when I divide it by n minus k factorial, it's still an integer, right? It's not obvious. But we proved that in the last slide when we said that, in fact, it was always the natural number, right? More than that, it's actually always a positive natural number or a positive integer, right? When you stay off of this corner case, when it ends up being 0 because it's k is too small or something is negative. So we have actually a proof of that fact. It's a nice inductive proof. It just wasn't obvious when we defined it using this form. Okay, so you could go back. I'm not asking you to. Okay, I'm not asking you to, but you could actually go back to that first project and then define n choose k in this new way. Okay, and then it would easily prove that n choose k is a non-negative number. Okay, all right. I mean integer. Okay, so let's go back to the taxicab example. Okay, so here's the recursive function that we have, right? And now that we see it, we see that this is very similar to n choose k, right? I mean, it's got that structure. I go up diagonally and then I go straight up. So it shouldn't surprise you that in fact this ends up being just a choose. Okay, and here it is. What we're doing is we're choosing 4 minus y ways, okay, of getting 10 minus x plus 4 minus y. Okay, now let's look at this a little bit more carefully, because here's what I'm going to tell you is the path. Okay, the path always has the same length because I need to go from here to here, right? So I need 10 easts, okay? And I need 4 norths, okay? That's always what I need to be able to get there from A, right? From any other place, I need 10 minus x east, okay? And 4 minus y's north, okay? That's how I'm going to get there, okay? And then what I have to do is choose where the norths go. Okay, so for example, 1, 2, 3, blah, 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 that. I might go east, east, north, east, and so on. Or I might go east, north, east, north, and so on, right? But I have exactly 4 norths and 10 easts that I can put in there, right? So that's really where this comes in, right? It's that choose kind of notion. Okay. So I've appealed to your intuition. Okay, I've appealed to your intuition by saying that n choose k, right? And it's that choose that makes it your intuition, right? Is how many ways can I choose k things out of n? Okay, so how many ways can I choose 4 norths out of 14 slots, right? That's the answer to the taxicab problem. So now I want to justify that, right? So how many different subsets of S with 3 elements are there? And we've done this problem to kind of give the idea, right? And it ends up being 10 choose 3, which is 10 divided by 3 factorial divided by 7 factorial, or 240, right? And remember how we got there, right? I pick one of the elements, right? And I say, okay, so now I need to choose n minus 1, 2, right? Because I already picked one, plus n minus 1. I'm not going to take that one, so I got 3 to select. Okay, it's the same recurrence relation as n choose k, and that's why n choose k is the number of subsets of a given size, like we claim that it is. Now, here's a slightly more complicated question. Okay, how many different subsets of S are there? I'm not talking about 3-element subsets. Okay, now we counted this before, right? Because we said choose A, and so we went like that. And here we would ask the question: do we include B? And so we went like that. And so we decided that the answer was 2 to the 10th, because for each element I had to make a choice. Do I include it or not, right? So we know that the answer is this, okay? But here's the different way of finding that same answer, okay? What I'm going to say is that I'm going to count the different ways using the choose function. Okay, so 10 choose 0. Okay, this is I have all of these subsets of size 0, and this is all of the subsets of size 1, and then at 2 and 3 and so on until we get to this, which is all of the subsets of size 10. Right? So you see that this also counts the number of subsets, right? I'm just organizing the count differently. I'm saying, okay, go ahead and get all the subsets of size 0, get all the subsets of size 1, 2, 3, 4, up to 10. That's all of them, right? And because they're disjoint, right? A subset can have 0 elements and 5 elements at the same time, right? Then I can just use my sum principle and say the total number of ways is add up each one of those, okay? So that's fantastic, but then what does that mean? Okay? What that means is that that sum has got to be equal to 2 to the n, because I already argued that the number of subsets total is equal to 2 to the n, right? So, so let's go back to Pascal's triangle, okay? And remember that if I look, for example, at this row, right, what I have is n choose 0, n choose 1, n choose 2, n choose 3, n choose 4, okay? So let's add those. 1 plus 4 plus 6, that's 5, 15, 16. Okay, how about this one? 4, 8, right? How about this one? 4, 2, 1, 32. You see that if I actually add each of the rows, I really do get a power of 2. So yes, that appears to be true. Okay. All right, back to functions. I have a set that has 10 elements. How many different functions from S to 0, 1 are there, right? And here's the way that I'm gonna kind of count them. Okay, so okay, so I have a set here with 10 elements, and the question is how many functions from that set to 0, 1 are there? Now again, we've kind of done this before, right? So here are 10 elements, and I can choose 2 ways here to assign that first element, 2 ways to assign the second element, and so on, and end up with 2 to the 10th. Okay, so we've seen that, and I mean here total functions. Okay, if I'm allowing partial functions, then it's 3 to the 10, because it could be 0, 1, or nothing. Okay, so I know what the answer is. Okay. All right. So imagine that I have a set with 10 elements. Okay. How many different functions are there from that set to the set 0, 1? Well, remember we kind of figured out the answer before, and what we said is, okay, here are 3, 4, 5, 10. Okay. So how many ways can I fill this guy in? It's going to be 3. Okay, and the reason is that it could be 0, 1, or nil, right? You know, for it's a partial function. It doesn't actually take it anywhere. This one is 3, that one is 3, 3, and so on up to 3. So the total number of ways is 3 to the 10th. Okay, that's the number of functions, including partial functions. Okay, but it's the total number of functions from the set S to the set 0, 1. All right, I'm going to count those in a slightly different form. And here's what I'm going to do. What I'm going to say is, these are all the subsets of size 0. Okay, and what I'm doing is when I take a subset, and I'm saying those are the elements of S that I'm actually going to assign a value in 0, 1. Everybody else is just going to be nil. Okay, so for those, now the question is how many different ways can I assign each element to 0, 1? And the answer is 2 to the 0, because there aren't any, right? This one's a little easier, right? 10 times 1, that is the subsets of size 0. I mean, of size 1. Okay? And then the question is, if I have a subset of size 1, there it is, right? How many ways can I fill that in? Well, it's either 0 or 1, so there's 2 ways, okay? and so on, right? So if I have, for example, here 10, 4, right? Then those are all of the subsets of size 4. There they are, right? And to each one of them, I can assign 2 different ways, right? So it ends up being 2 to the 4th, right? And this is the last one. How many ways can I get 10 elements out of 10? By the way, there's only one way. Then I can define 2 to the 10 total functions for those 10 elements. Okay, so that's a different way of counting it. So again, what have we just shown? We've shown that this left-hand side, right, has to be equal to 3 to the n. Okay, shoot, that is not at all obvious, is it? Okay, I mean, I would be hard-pressed to give some kind of an intuition as to why that's necessarily the case. But I think this argument makes it absolutely necessary. Okay, so it's a proof. They call that combinatorial proof. I count the same thing in 2 different ways, then those 2 different things have to be equal to each other. All right, so let's end with this example. I have a plus b, and I'm going to raise it to the 10th power. And so the question is, what is the coefficient of the term that has a to the k, b to the 10 minus k, right? And what we're doing is we have a plus b times a minus b, I'm sorry, times a plus b, right? And this is 10 times, okay? And in order to get a term that has a to the k, b to the 10 minus k, right? What I have to do is pick an a, pick a b, pick an a, and so on, right? And eventually pick an a. I need to pick k a's, okay? And that means that I need to pick 10 minus k b's, right? That's just, if I don't pick an a, I have to pick a b. All right, so how many ways can I pick KAs out of 10 things, right? I got to pick KAs out of each one of these terms. And the answer is obvious, is 10 choose K. That's exactly what 10 choose K is. So that is the coefficient. The coefficient is 10 choose K. So that's called the binomial theorem, okay? The binomial theorem tells us what the coefficients of each one of those terms are. And basically, you know, it's written like this: a plus b to the n, right, is equal to n choose 0, a to the a to the 0, b to the n, plus n choose 1, a to the 1, b to the n minus 1, plus n choose 2, a squared, b to the n minus 2, all the way to n choose n, a to the 0, b to the n. Okay? Oops, I'm sorry, a to the n, b to the 0. Okay? So that's the binomial theorem. And don't forget that. We're actually going to need that in one of our future slides.